Hello community, there's snow is beautiful out there. If you want to go skiing, do it now. But before we have to look here how to optimize your AI system. And we're going to talk about optimization for your LLM and multi-AI agent system. And here we go. And you know this, no? You have multiple LLMs, GPT-4, Claude, Gemini, Llama, whatever, who cares? And you have different benchmarks like live code bench or common generative data set here, the hard version. And you have different performances from single LLMs or vision language model. No, you know this. Or here, simple question and answer data set, where you have 4,326 short facts here. And you see, my goodness, the performance is almost zero, no? Or you go here to other ones where there's a beautiful saturation. But this is not important. You know what is important? This is important. Then we have other benchmarks, like table arithmetic or table bias. And here you see all the models are almost at zero performance, except if we combine those LLMs that have zero performance in a particular way, in both cases we achieve 100%. So what is the miracle that is happening here? And is this possible at all? So let's open up this video. So multi-AI agent system. So you know, in our agent we have a LLM. We are not rule-based, and I showed you here, for example, here 9 DeepSeek agents here augmenting a knowledge graph. Or if we go here with Google Stanford, the co-scientist, we have 6 agents plus a supervision agent. And I talked to you about here a memory agent for a crystalline structure. Or we go here with a multi-agent graph rack system. Multi-agent is the future. No discussion about this. But you know, let's make it simple because it's such a beautiful day today. What about the simplest configuration? Let's take the 3. Just 2 LLMs. Well, a locate and a solve. Then we have a self-refine configuration where we have here, we generate something, we critique it, and we refine it. And then let's go for a very simple multi-AI agent debate structure where we have here from the generative AI 1, 2, 3 ideas, and then there's a short discussion going on, and then we have a consensus. Couldn't be easier, no? You know what's amazing? Look at this. If we have now, and let's go here and let's take the simplest case A. So we just locate here the query and then we solve it, no? Couldn't be easier. So we have here anthropic and anthropic. So the first one of the task is easy. This is the simple task, no? So we do it and then we solve it, and the solve is wrong. Or we take Google and Google. No, and you think, yeah, the Google will work. No, okay, it's Gemini 1.5 Pro, the old one, but never mind. No? Now, look, here it fails in the first run, in the first element, but it can solve it, but it did not understand the question. But you know what's crazy? So both answers are wrong. If we combine this, that we choose now a particular LLM for the first part and a particular LLM for the second part, although we have 2 wrongs, this now delivers here the correct answer. And this is done by LLM Selector. This is a new method, and this is the topic of my video today. And I thought, this is simple crazy. Why nobody thought about this before? And you might say, hey, wait a minute. If you want to combine 2 LLMs that already did provide wrong answers, suddenly a multi-AI agent system can now deduct the correct answer? Yes, absolutely. This is it. And you might say, who had this idea? Well, it's easy. Microsoft, Stanford University, Princeton University, and UC Berkeley. Great. But you say, hey, wait, we don't need all this multi-AI agent system. Come on, it's too expensive. I don't know what it is. I have not watched your video here. What is a reward system? I know nothing. But we have modern VLMs, vision language model like Grok 3, no? This is it. This is all we need. I know that you think Grok 3 here is the smartest. I know, but you know what? This is just the marketing. So let's test Grok 3 on this simple arithmetic expression we just saw in the simplest test, in the simplest configuration. And this doesn't even require any form of advanced reasoning or logic. This is just Grok 3 pure. So we have exactly the same question. Hey, what is a particular number plus? And then we have an arithmetic expression, and we compare simply 2 numbers. And you have, yeah, this is it, and yeah, calculation, and the answer is 48. And you look at this, and you see that this is the wrong answer. It got everything right, except it doesn't know which of those two numbers is greater than the other one. So the arithmetic operation is wrong. So Grok 3, given the simplest kind of complexity, fails already here. And now you understand why we cannot use Grok 3, and I don't use Grok 3 anymore for any physics or chemistry or medical or financial operation, because simply cannot solve this task. It solves it in the wrong way. So we have to choose another LLM. No problem. We have 100,000. I don't know how many LLMs you have. Let's go here for O3 mini high, See, absolutely the same. Yep, 49. This is the correct answer. Great. So we take this LLM. That's all there is. This is the whole, I don't know, whatever complexity. We just choose the right LLM for the right task. So we subdivide the complexity into simple tasks, and then we choose for the right model that can solve the task. And I don't care if it's OpenAI or X or Grok or what the hell. I don't care. I just want performance. And of course, price is another element, but more about this in 5 minutes' time. So here we are. Here we have our spark of genius. So what do we do? As a first step, the authors here, Harvard and everybody, told us here systematically study model selection in a static compound AI system. Those where the number of the modules, the sequencing of module calls, and the mapping between the models and the models are fixed. And in this context, they found here as a first idea that allocating different LLMs to different models really, surprisingly, lead to substantial higher performance than allocating here the same LLM to all the models. This is amazing. I never thought of this. I thought if I go here with the biggest, the most expensive LLM, I put this LLM in all my agents, in all my models, no? Because I thought, hey, they have the best performance. And you know what? It turned out to be wrong. I was wrong about this. I just have to find the right LLM for the right subtask. And you know what? This right LLM might even be cheaper. And I can run it locally. I don't have to pay here a cloud provider. I want to give you an example. Next example here. The next most complex here is self-refine. Yeah? We have a critique and a refinement step. So I thought I have here the same LLM. Let's take Grok 3, for example. And you do the test and you find it fails. So consider again to self-refine here a multi-agent system consisting of 3 models, a generator, yeah, a critique, yep, and a refiner. Great. So LLM A that we have here may be better at providing feedback, but much worse at generating and refining answers than LLM B. So in this case, allocating LLM A for the critique and LLM B for the other 2 is better than allocating here one for all the modules. So what we just have to do, we have to find out which model is best for our task. And if you think about a multi-AI agent configuration, this could not be so complex. No, it just goes with factorial. Okay, third example, multi-agent debate. You know this. The agents here debate among themselves who has the best idea, who has, I don't know, the greatest solution. This is called the model selection problem. Careful, this is MSP, not MDP. So not the Markov decision process, but MSP. So we design now, I mean, the authors know from Princeton, everybody, we design now an LLM selector. This is a simple framework that optimizes now the model selection problem for any static compound AI system given here a particular training budget. Time, money, whatever you have. And the LLM selector now iteratively nominates one module and allocates it to the LLM with the best model-wise performance as estimated by another LLM. And this other LLM we call an LLM Diagnoser. Beautiful name? Okay, let's go with this. So we have 2 LLMs and this is their job. Couldn't be easier. Let me give you an example because it's always so nice to see an example. No? We have here a question, never mind, and then we have here a debate of our AI agents. No? So we generate here 3 answers, and let's have the case that we generate 3 answers with GPT-4 Omni. The answer is 8, and the answer is 8, and the answer is 8. Beautiful, temperature is 0. And then we debate. And we have 3 GPT-4 Omni debating here the same answer. You know what? They come up with the wrong answer. So it is not a good idea to use the same LLM here for all the different agents and all the different modules. You know what's much better? Look, GPT-4 Omni, okay, but the next one, Gemini 1.5 Pro or Gemini 2.0 Pro, whatever you like, or Llama 405B, doesn't matter, just give it diversity. And then for the debate, we still have, like here, the GPT-4 Omni. So it's the same still stupid GPT-4 Omni that has here the debate between itself. But now different models provide different outputs, and you know what? It is able to find the correct answer. Check. Isn't this amazing? I find it absolutely fascinating. Yeah, for the definitions, always, what is an LLM module? A module utilizes here an LLM to process the inputs, typically concatenates all the inputs to a text snippet, obtains an LLM response to the snippet, and sends the response as an output. We can now, in the mathematical description, see this as a graph, no? Why? Because we have a compound AI system of our multi-agents, and of course you can see this with vertices here and with edges. So we could theoretically have here a graph theoretical and mathematical approach, and there's all the notation and the definition, but you know what? I want to show you this simple way. I just want to give you the feeling for this. I want to explain it to you, maybe without math. So, this LLM Diagnoser, this secondary LLM that judges here the modules. Let's have here a direct flow through the problem. So, we have now simplest case, no? Locate, solve. This is it. Evaluating the solve module with Claude 3.5 Sonnet. I know you love coding Claude 3.5 Sonnet, would get an input. We have the same fascinating question. You know the answer should be 49. And then we have the locate module output. And this is simply here. This is what is 48 plus and this expression. So we correctly extracted, let's say from my human prompt here, we located here exactly the problem, we formulated him, and great. And now the LLM just has to solve it. Now we come now to the solve module. The output of the solve module, if we take Claude 3.5 Sonnet, the latest one, correctly outputs 48 now as the numerical mathematical solution. It's because it simply makes a mistake. So we have a final output of this system now, combined 48, and which is incorrect. I know you're not gonna believe this, so I just went there and said, okay, Claude 3.5 Sonnet, the latest version. What is exactly this expression? And it's 48. So this is incorrect. Now what happens? The LLM Diagnoser analyzing this would see that the locate module did the job correctly. It took my prompt and it understood exactly here that it has to solve this particular task. Now the solve module outputs 48. This leads here to an incorrect mathematical verifiable final answer because it should be 49. So now if we have here, if you want the diagnoser, and let's have a diagnoser that is a little bit more intelligent than Sonnet and can solve this, it understands that Sonnet is the wrong model for the solve module here in this particular case for this particular task. So now the LLM Diagnoser would reasonably judge the following. The solve module with Claude 3.5 Sonnet 2024, 10, 22 seems to be contributing to an error in this case. And now understand that this is a simplification in a certain sense. Because yeah, this is wrong. This is absolutely correct, the judgment. But we are just making now a simplification that we say now with our diagnoser, we just go for a binary decision, correct or incorrect. We don't go, hey, this is 70% correct or something. So we just have binary, yes, no, enter, don't enter, finito. Great. I want to show you the prompt because you might say, how can I code this? No, in a diagnoser prompt, this is the code here. This is the prompt. You talk here in a system prompt, the error diagnose expert for a compound AI system. Yes, you get the idea. No problem. So let's come to the core of this publication. This LLM Selector is now specifically designed to avoid trying out all the possible configuration in a multi-agent system or any compound AI system, and it uses here this a particular, if you want, this particular solver, this particular diagnoser for this task. So this is, if you want, the trick to this model. Because we have here a system architecture that could be like this for our multi-AI agents. And now we have to find the right model for the right subtask that is defined in the consortium, in the interplay, in the interconnects here of the complete AI system. And this would be here the perfect optimized model allocation to our specific subtasks. Now, if you want to know a little bit more, let's just stick with me for 30 seconds. If not, skip ahead for 30 seconds. How this is done in detail, let's have a closer look. So we have our LLM Selector, and what it does is a model-wise iterative optimization. So instead now of considering all possible combinations simultaneously, our selector breaks down the problem into a series of sequential, module by module optimization steps. So this depends here on the quality of the LLM you use here for the selector. So I would recommend going here for, let's say, mathematics or your domain knowledge for the best model in your domain. So the LLM selector focusing on optimizing one module at a time, keeping the model allocation for the other models temporarily fixed. So simple, if you want estimation, everything is fixed, and we have just 1 degree of freedom for this particular module. Then we have a guided search in the search space. Then we have, within the selector framework, the LLM Diagnoser. And it does not empirically test every possible configurational whatever. We're running here full end-to-end system evaluation because it would be too costly if you have multiple systems. So instead, and if you want, this is the trick or the beautiful thing here, it uses the LLM Diagnoser to estimate the model-wise performance, and I have shown you this on the example already. In mathematics, it's easy because it can calculate if this is right or wrong. In code, you can have it here simply, do you run the code and see is it working or not? If you have a little bit more causal reasoning, it might not be that simple. So interesting, but this LLM Diagnoser estimates here the model-wise performance of different candidate models, and this estimation is much cheaper than here the full system evaluation. If you want, you can do the full system evaluation, but all the authors here tell us, hey, it is maybe not really necessary to spend this much money because we have here this directed search. And if you remember my other one about the reward system here to optimize here in the TTS and the test time scaling here, we had the reward model, and now if you want, the diagnoser is kind of our guiding star here in the search space. So the LLM Selector uses now the diagnoser estimation to guide its search in this open search space, selects the model, yes, directed search strategy, beautiful intelligence, yes. And then, of course, you have a limited number of evaluations, depending how much money you want to spend at the time you want to wait. Let's say you have K models, and yeah. But remember, it does not try all theoretical possible combination of all models for all modules. So there is a tiny but exists here certain inaccuracy because it's not really testing out all the knowledge, but here we depend here, if you want, on the intelligence here of the diagnoser. Of course, we can calculate this for known models, and here you see it for our 3 cases. Here in this 2, this is the simplest case for locate solve. Here we have our refine with our 3-step, and here in this 2 we have here the debate structure. So you know this, and here we have all the models. Whenever you see this, please fill in your models that you have. I give you the code so you can have this immediately for all the different benchmark. What is interesting, and I just coded here DSPy, you know, if you want this next step after code engineering, code optimization, prompt optimization, and then text grad, you know, it is performing better than DSPy. It would be interesting to see text grad here, but this LLM Selector has really an outstanding performance if you compare it here with all the different benchmarks. So interesting. I definitely will use this, and I'll give you the code in a minute. So there we are. We are now here with the facts, and you have here this beautiful publication, Microsoft, Stanford, Princeton, and Berkeley, February 2025, and they have here this idea that they say, you know what, we should have here an optimization to select the best LLM for the best subtask. Great idea, absolutely amazing. So if we apply this now for our own, what we do, first you define your set of vision language model you want to integrate, you want to compare for your multi-AI agent configuration given your specific task. So maybe you define your local LLMs that you have on your machine or whatever you are in your particular cloud as your preferred set of AI agents. Or maybe you sort your preferred LLM according to the cost, to the pricing here for cloud inference in your region. So however you define your set here of LLMs or VLMs, this is up to you. And then you simply run this code that is here given here to us by the consortium. And beautiful. So just days ago it was optimized. This is great. We have an Apache 2 license, so we can use this. And they really give you beautiful examples. Look, quick start, no API key needed. You have, for example, the live code bench dataset. You can evaluate here the first refined system using here the fixed models. The expected outcome then for those three is here you have now a numerical score given. And if you run now the LLM Selector to optimize the system, this is just here 6 lines of code. And then you see, yes, with 95%, this is much better than 86, 89, or 86%. So this shows you here a performance gain you can have with, I don't know, 5 minutes of coding. Of course, you can customize this, and I was asked to talk a little bit more about code. I thought if I give you the GitHub, it's enough. Okay, no, here we show you. Customize system and task, API keys needed. So if you have, I don't know, Anthropic or Together AI or wherever you are, or you pay for Gemini or you pay for OpenAI, wherever you have your keys, great, you just have it. Look, this is the way to go. They have the Python files for you. They have the Jupyter notebooks. Everything is there. And they're even so kind. Imagine they say, hey, can I request a feature? And they ask you, yes, we are happy to hear from you. Please feel free to open an issue for any feature request. We will also be happy to coordinate an ongoing effort. Please send an email. It is now open, available, 21st of February 2025. The code base, you have more examples here in the GitHub. You have demos in the GitHub. Have a look yourself. So I think some great work, beautiful, coming to an end. Yes, try it out. I definitely will. And I already started. I think it's so amazing. Now, if you think, hey, yeah, we go here for an hour and it is only about, is this Grok 3 or is this, I don't know, OpenAI 05 or whatever is coming up? I don't know. It's not about a single model. It is about an intelligent combination in a multi-AI agent system configuration. And you see, with a little bit of a mathematical optimization like LLM Selector, you can reach 100%. I think this is simply amazing. So we do not depend here on single LLMs or single VLMs. I hope you enjoyed it and maybe you decide to subscribe. Then I see you in my next video.